upload the assignment first, and some of the students asked me some question about the assignment, but some of the students had some problems when they try to upload the data set in Veka. During the last section, 1 hour ago, for group 1, I have tried to share my screen for them and talking about the problem and talking about Veka and how I can use Veka. Unfortunately, my network link was not stable, and when I share my screen for them, they received lots of errors. So I decided to change my way, and for Veka, I will record a video soon. In that video, I will talk about the problem happened for you and how can we use Veka for the first assignment, how we can use them. But no. So about the problem discussed in the WhatsApp group yesterday, I will give you a video record in the near future. And after that, if you have any question, you can ask me in the WhatsApp group. Okay? If someone has problems about the discussed content in the past sessions, please ask me. If you have any problems about the content, please ask here before starting the new content. Okay. In the last session, we talked about pre-processing. As we said, data mining is very important, and all data mining techniques are affected by data. The result of data mining is directly affected by data. So if I use incorrect data, the results will be incorrect too. In these cases, we need to use pre-processings, and in the last session, we talked about pre-processings and how to handle missed values. Today we will talk about noisy data. But the first question is that what is noise? Noise means a random error or a random error that is applied on measured values. I have a gathering information system starting from a collector which collects data, and then this data is transferred across a network. Then it's stored in database, and Then I will retrieve the data to handle them and applying data mining techniques. During this system, starting from the collector until inputting data in data mining tools, a noise may applied on my data. Maybe my data collector has some problems and some faults. It has some faults and making some errors in data. Maybe the entering system has some problems, and when a human, for example, enters data, the enter data had some problems. Maybe the transmission service has some problems. Maybe the technology that I'm using has some problems. Maybe some inconsistencies between different sources of data may cause some problems. For example, when I'm talking about technology limitations, let's suppose that I have a feature that its type is numeric and its length is 2 byte. Okay, I have a 2 byte variable. I have a 2 byte attribute. Okay, when I'm using the 2 byte length attribute, then values between 0 to 0 to 65 535 can be entered into this attribute. Only the values between 0 to 65,535 can be entered into this attribute. But what will happen if I try to put, for example, values 100,000 into this attribute? It's completely clear that part of my data will be lost. Why? Because this attribute has not enough space to keep those data inside itself. It has not enough space. It's a big problem. And the length limitation makes a big error on entering 100,000 in the field, and something else is stored in database because the feature has not enough space to keep those information, and overflow is happened, and the result is wrong. The result is not incorrect. Sometimes, for example, I have a feature with a specific name, for example, name A in one database, and I have a similar feature in another database with name B. I should be care about their names. A and B are similar features, but their names are not. Maybe their names are same, but their types are not the same. For example, I have a rate feature in database A and another rate feature in database B. But the type in the first the type of rate in the first database is numeric, and in the second database is nominal. Maybe I have two attributes in two different database or data sets with a similar name. For example, if I have for example, I have a feature named length in database A and another feature length with name length in database B. But they are not the same. For example, the length in the first database is for length of a human, and in the second database, the length is related to length of, for example, a table, something like that. Maybe one of them is in meter, and the second one is in feet. Their metrics, their scale are not the same together. So when I'm entering data into such cases, into such data sets, it's clear that some values are incorrect, are not recorded correctly. Maybe my network platform has some problems and the data is affected during the transmission in the network. So their values can be changed during transmission. So always I should give some chances for changing in data. My data is my data correct? Yes or no? Other problems may affect this situation. For example, when we have duplicate records, there are some duplicate records. In one record, we have item X, and in the second method, in the second record, a duplicated record, we have item X, but its value are not the same as the values in this first record. Sometimes data are not complete in different features, in different records or tuples or instances. Sometimes my data are not consistent when I'm trying to use different sources of data, multiple sources of data. The data are not consistent. All of these problems make a noisy data. And as I said, noisy data will affect my results, my data mining results, will making incorrect them. So one question is that, okay, I have a noisy data, I accept it. Okay, but how can I handle noisy data? To handle noisy data, we can use different methods. Here in slide 10, we introduce four different methods for this reason. The first one is using binning. When I'm talking about binning, suppose think about histogram diagram. Histogram diagram was a simple diagram, as we discussed in chapter 2. It's a simple diagram with some columns. Each column has a specific void, and my data are put into these columns. Now we say bins instead of columns. We say bins. So in binning techniques, firstly, I should sort my data ascending. Then I should partition those data into some bins, similar to histogram. When I'm trying to create a histogram, I have to create some bins, some ranges for each column. Okay. In a similar manner, I'm creating some bins and putting my data into those bins. Then in each bin, I can replace the values in that bin, values in that bin with, for example, mean value or median value or lower bound or upper bound of that bins. Replacing values in a bin with mean of those value in that bin, or with medium of values in that bin. I'm replacing those data with mean, with medium, with median, with boundaries, maybe lower bound, maybe upper bound. It's an approach to handle noisy data, to remove noisy data. I'm not sure, maybe this removes some noise, and maybe it makes some errors, maybe, but most of the times this is smoothing, applying, replacing a value with mean, replacing a value with median, replacing a value of, for example, with a lower bound or upper bound in a bin is a good option. And it has some benefits for me. So using binning is a good technique to handle noisy data, because I know that my data in a normal situation, my data is placed in a specific interval. So when I replace a value with mean or median, I'm trying to apply my idea that the data should be placed in a specific range. I'm trying to apply this rule. The second approach to handle noisy data is using regression. When a noise is added to a data, the deviation of that data from, for example, the mean of data, the deviation of that data is increased when a noise is adding to a data. Its deviation will be increased. The regression techniques estimate a formula for a line. Let's suppose that my data are placed in a space, or in a 2D or 3D space, and the regression estimates a formula for a line between those points in the space. This line has minimum distance from those points. So when I'm using regression technique, I'm trying to use a line formula instead of using values of those data. It means that I will replace a real value of data with the nearest value in that line. Instead of using a data point, I'm using the nearest point, value of points in that line, that estimated line. So it can smooth the spreading of those data. Regression is the second technique to handle noisy data. The third approach is using clustering. Clustering means that I am trying to put data in a data set, to put data in different classes, in different clusters, in different groups. Okay. After creating these groups or classes or clusters, I don't know. After creating these groups and putting data into those groups, we can see that some of data are grouped in some, are entered in some groups, and most of data are entered into some other groups. In such case, I can say the groups with small number of items, the groups with small number of items are outliers. So simply I can remove them. Because as we show in chapter 2, outliers can affect the results, especially the statistical results. So simply using clustering techniques, I can find the outlier and trying to remove them. Outliers are inside the groups that their number of items in that group is small. So clustering is another option. The fourth approach is using an inspection and using cooperated inspection, cooperated with computer and human. Computers handle data, and also a human handle the data too. It's a double checked. The data are double checked by a human. It's another approach, and someone can use this approach. Okay, so as we see, the data cleaning is a big process. It's not just a simple task, it's a big process. How we can do this? To applying data cleaning, firstly, we should define for a machine, define what is an outlier or what is a noise. How? For example, for a nominal case, for a nominal attribute, I can define the set of uh, values, set of possible values. For example, for gender or sex, I can say that the values of gender, attribute gender, is male and female, and nothing else. For nationality, I can say that the nationality can be, for example, Irani, in Iran, uh, Iranian, Iraqi, or something like that. That total number of countries in the world are about 200 countries. So this set is limited. In some databases, in some cases, when the database is created, for each feature, the designer of that table or that database, for each feature, add some metadata. Metadata means data about data. For example, for age, for attribute age, the designer can says that okay, the age is something between 1 and 100. For example, the age can be in the range of 1 to 100. This is an information, a metadata. Right now, I know that the age cannot be, for example, 150. It's outside of the range 1 to 100. This is a metadata. For example, if I'm talking about the weather can be sunny, the weather can be cloudy, the weather can be semi-cloudy, maybe it's windy. There are some possible and limited items. So the set of possible options, possible choices, possible answers to that attribute is limited. Is limited to a specific domain, to a specific range, to a specific with a specific distribution with some dependencies. So we can use metadata in to find noise, to define noises or outliers. The second one is checking field overloading. For example, I say that maybe an integer with 2 byte length is used, and if I enter a bigger value because of limitations, it has it records a value, an incorrect value. It records an incorrect value. So field overloading, checking a field overloading can be useful. Maybe I should check the business rules. Some rules are affected together. Some rules are related together. Some rules are unique. Rules must be unique. What about null rules? Can we accept null values in my data sets? In some cases, yes. For some attributes, we can accept null values. But what about the rest of features? In some cases, we cannot accept null values. Sometimes we can use some commercial tools, for example, data scrubbing or data auditing tools, to analyze data, to find domains of those data, to find errors, to find some relations, to correct data. Data auditing tools are very useful in this case because they are trying to find uh, different relations between different values. However, they are uh, their processing is not simple, uh, and they need lots of processing. They need lots of processing power. They have a big processing overhead. Okay, to find correlations or maybe clustering and someone else. Sometimes for data cleaning, we need to migrate data, changing a data from one type to another type. Maybe we need to combine some data, integrate them. How we can do this? It's a cleaning process. You can use uh, commercial tools, or you can do it by your hand or writing a program. I don't know. But sometimes migration and integration can clean the data. Sometimes can clean the data, and some data will be removed. Some incorrect data can be removed in this case. Sometimes we can use some interactive or iterative techniques that using both uh, techniques, migration, integration, uh, discrepancy detection techniques. Okay, so data cleaning is an important task for us. The second task, or the second major task in pre-processing, is data integration. Data integration is a necessary case when we are working with multiple sources of data. I have different sources of data, and I want to work with them. I need to combine their data together to create a big picture from those data. In the past, you had a lesson, database lesson, and you learn how you can use select, for example, select SQL command select, to combine different tables. For example, you can say that okay, combine two tables according to their customer ID. In table A, customer ID feature is named as cost-id, and in the second table, customer ID feature is named as cost-number sign. In this case, I have two same features, but their names are not the same. Their names are different. So when you are trying to combine data from multiple sources, you should be care about features, similar features in different sources. Maybe their name are different. Maybe their type are different. In some cases, maybe everything is similar, but the values, some cases have different values, different acceptable values. For example, I have two different sources. In one of them, we have a record for Bill Clinton, and in the other table or data set or database, are they same? Yes or no? Bill Clinton is the same is William Clinton? Yes or no? It's a big problem. How can I detect these conflicts? How can I resolve these conflicts? In some cases, we have different sources of data with different attribute names. Those attributes have similar names and similar types. And there is no conflict between them. In some cases, attributes are the same together, but their names are not. Or maybe their attributes are not. Their type are not the same. Maybe their type are the same, but their scale or their metrics or their representations are not the same. For example, I have two feature lengths. One of them is in meter and the other is in feet. For example, someone says that, okay, this length of this table is 2 meters, and then the other says that the length of this table is 7 feet. They are the same, but 2 is different from 7. Why? Because the first one is 2 meters, the scale is different, the scale is in meter, and in the second one, 7 is in feet. So we firstly need to scale these meters, we should to change these scales. make them similar together. Sometimes we need some reasoning techniques, changing the values before applying data integration. Another problem in data integration is redundancy. As I said, data integration is happened when I'm talking about handling data in multiple sources. Okay, I'm talking about handling data in multiple sources, and I'm trying to integrate them. I'm trying to combine them. In such cases, maybe, for example, I have two bank accounts. In a similar bank, I have two bank accounts. One of my bank accounts is in the city A, and the second bank account is in city B. For example, my bank is, for example, Tejarat or National Bank, for example. But I have a bank account in National Bank in city A and another bank account in National Bank in city B. The question is this. The first branch of bank gives all of my information. They has my information. They have my information. My name, my family, my national code, my address, my phone number. They have all of them. And in the second branch, they also have my information too. In such cases, how the national bank can define that I have two different bank accounts, one in city A and one in city B. My data are redundant. My data is added in two different tables. One table in branch A and the other table in branch B. Okay, the answer is that I have to use an object identifier or an object identification. For example, they can use my national code as a primary key in their datasets. As a primary key. Because my national code is unique. So they simply search for my national code in different branches. Or maybe a primary key can be a combination of some attributes, not one standalone attribute. Maybe a primary key is a combination of some attributes. Okay, it's not important. But I know that this primary key is the identifier of a specific object in different databases. And then I can make a relation between those data. It's really important. For example, in branch A, maybe for example, they give my name and record my name correctly. And in the second branch, by mistake, they made a mistake and they record my information with a mistake, with an error. Okay, but the national bank can identify me just using my national code, nothing else. Just using my national code. Then they can detect that in one branch they record a specific value. In the second branch, uh, they made a mistake. For example, my name is recorded something else. But the primary key is my identifier in their tables. Sometimes data are derivable. When I'm integrating data, the data are derivable. It means that, for example, I'm trying to calculate the annual revenue of a store. I have to calculate the revenue in different seasons and then give the summation and uh, present it as the annual revenue. It's a derivable attribute. Okay. When the data is redundant, it should be clear. When the data is redundant, for example, I have two different bank accounts. If I'm simply count, for example, number of customers in National Bank, I have a record in branch A and I have another record in branch B. So they simply count me two times. It seems it's not correct. Their system has problem. I'm a unique person, but I have two different records, so they count me as two different person. So the redundancy can affect the results, especially in derivable data. So, and maybe, for example, in the first branch, they record my name as Hossein, and in the second branch, they record my name as Hassan, just simply by mistake. They forget Ye in this case, and Hossein is changed into Hassan when they record my name. What will happen in the final report? I have two different names. One is Hossein and the other is Hassan. So finding redundant information is very important. Sometimes when I'm trying to do data minings, redundant some attributes have similar effects on my data mining algorithm. So if I be care about those redundant attributes, I can remove some of those attributes. Why? Because the attribute 1 has a similar effect to the second attribute with attribute 2. They have a similar effect. So simply I can remove one of them, and the other attribute have a similar effects. So the result doesn't change. But as I remove one attribute and keeping the second one, I reduce the amount of data entering into the data mining algorithm. It's very important. So during the integration, reducing the redundancies is very important. Most of times, data mining analyzers, data miners, applying data mining data reduction techniques to reducing the amount of data entering to the data mining process. At least, the primary benefit of such reduction in data is that increasing the speed of data mining techniques. This is the primary benefit. The amount of data is reduced, so the data mining techniques can be applied faster than previous. But in some cases, it's very important. In some cases, when we try to remove redundancy, using removing some attributes, maybe some records, maybe using integration and something like that. In some cases, even because of removing redundancies and removing inconsistencies, the quality of final results of data mining techniques will be improved too. It's very important. It's very interesting. In some cases, not all of cases, it's very important. In some cases, when we remove correlated attributes, why? Because they have similar effects. So we can remove them. When we remove correlated attributes from our data sets, the quality of final answer of data mining techniques will be improved. It's a side effect of reducing data, reducing redundant and correlated data. But it's presented in some cases, not all of cases. But in all of cases, by reducing the amount of data, we can decrease the total time needed for the data mining process. The technique can be applied faster than before because we decrease the amount of data. Okay. So it's a very important question for me. How we can find redundant attributes? How we can find redundant attributes? There are different ways, but two primary ways for this reason is correlation analysis and covariance analysis. When we are talking about correlation analysis, this is happen for nominal data or numerical. There are different, but they can be applied in a similar manner for both of these types. The first correlation analysis method is using chi-square test. Chi-square test is calculated in this way. Chi-square is equal to summation of square of differences between observed value and expected value in power of 2. You can see that the difference between observed value and expected value in power of 2 divided by the expected value. The larger chi2 value means that those variables we are testing for different values. The larger one means that those variables have more relation, are more related together. So for different cells, we can calculate, we can apply chi-square test, and we can find the value of chi-square. If this value is high, so I can say that those values are related. However, we should be careful that if we find some correlation between different attributes. I have two attributes and I applied chi-square test and I found that they are related. They have some correlations. Okay? But this correlation does not mean that there are some causality between them. It does not imply causality. For example, than number of hospitals in small cities, and also number of car thefts in large cities are higher than number of car theft in small cities. It's completely acceptable. But if I try to use chi-square in this case, I can find that, okay, if number of hospitals in a city became large, it means that number of car thefts will increase too. Or if I add more hospitals to a city, someone can say that because they are correlated. If you add more hospitals to the city, build more hospitals to the city, the result is that increase number of car thefts in the city will increase too. Is it true? Of course, no. There is no relation between hospital and car thefts. Car thefts is because of economic situation in the city or in the country. But number of hospital and hospitalities is something different. It's related to the health, human health. So I cannot say, okay, if you increase number of hospitals, then number of car thefts in the city will increase too. So I'm against to building more hospitals in the city. It's a joke if I said something like this. But if I apply a chi-square test, I can find that there is a strong correlation between hospital and car theft. I can find a strong correlation. So correlation does not imply causality. It's very important. Number of hospitals and number of car thefts are both related to the population. For example, number of hospitals and car thefts in Baghdad is higher than number of hospitals and car thefts in a small city in for example, in the south of Iraq or in the west of Iraq. I don't know. Just because number of people or population of Baghdad is higher than that city. Just because of this. So directly I cannot make a reasoning or this correlation does not imply something else. Just we simply calculate a number and say, okay, it seems there is a correlation between number of hospitals and number of deaths. Nothing else. You cannot make a reason according to this correlation. For example, let's suppose that we have some people, we are asking them, are you playing chess? Some of them says yes, some of them says no. We don't like chess. We don't play chess. Okay. And also we ask them, do you like science fictions? Do you read science fiction books? Yes or no? Some of them says, okay, I like it, and some of them says, no, we don't like it. We ask from we ask two questions. Do you like play? Do you play chess? And do you like science fictions? We ask these questions from 1,500 peoples, and the results are presented in this table. Here we can see that 550 people say that they like science fictions, and 1,050 people says they don't like science fictions. Also, 300 of those people say that they play chess, and 1,200 people say that they don't play chess. Okay. Here in the parentheses, you can see some other numbers. These numbers are expected values. We expect that, for example, 90 of those people that we ask say that they play chess and they like science fictions, but in reality, 250 people say yes to both of those questions. In not playing chess and liking science fiction, we expect that 360 people say place in this case, not playing chess and liking science fictions, but only 200 people place here, and the rest of other values in this way. Okay, we have these results here, and I'm trying to find that I want to find that is there any correlation between playing chess and liking science fiction, yes or no? I'm, I'm deciding to find this. Okay, according to the formula, I'm placing the numbers here in this way, 250 minus 90 in power of 2 divided by 90, 50 minus 210 in power of 2 divided by 200, and so on. And the result, the chi-square, the final chi-square value is 507.93. It's a big value. So based on our knowledge, we can say that there is a correlation between liking science fiction and playing chess. Just we can say that there is a relation between them, nothing more. So this case shows this, that both of these questions or both of these features are correlated. Okay, we have another correlation matrix for numerical data, which is we called it correlation coefficient or Pearson product moment coefficient, yeah, or Pearson coefficient. Its formula is written here. You can find it. Here. And in this case, A bar and B bar are mean values of record A, values in A and values in B. There are two features. The average values in the first feature is A bar, and the average values in the second feature is B bar. N is number of total number of features or records, and AI and BI is the value of different value of those uh, features for a specific rows or for a specific feature, and sigma A and sigma B are standard deviation in feature A and feature B. Okay, you can calculate using this data, using number of attributes, number of features, excuse me, number of samples, values of different samples, mean value of different features, and standard deviation of those features. You can simply calculate the Pearson product moment coefficient or correlation coefficient. This value here, we are using a minus here. This value can be a positive value, can be 0, or can be a negative value. It's something between -1 to 1. Pearson product is a value between -1 to 1 plus 1. If R is equal to 0, if R or relation between A and B is 0, it means that A and B are independent. If R is a positive value, it means that A and B has a positive correlation, and if it's less than 0, R is less than 0, A and B has a negative correlation. As we discussed in chapter 2, positive correlation means that if A values increase, the B values are increased too. A is increased, B is increased too. This is a positive correlation. In negative correlation, when A values increased, B value decrease. They are against together. Let's have a visual example here. Here, you can see that the correlation can be the Pearson correlation can be between -1 to +1. In -1, we can see as soon as increasing in the value of one feature, the value of the second feature is decreased. And in +1, you can see that both the value of both of features is increased together. Also, you can find some other correlations here. It's a visual correlation. You can see that as long as you are moving from -1 to 0, 0 is here, this one. As long as we are working through -1, from -1 through 0, you can see that the sparsity of the data points will is increased. And when we are working from 0 to +1, the sparsity is decreased. You can see. So when we are talking about correlation, it means that does two different attributes have affected each other, have similar behavior? Here we can see in positive or negative correlations, adding increasing in one of them will increase or decrease the second one. They have a very specific behavior related together. They are completely related together. They are completely related together. But when the correlation is 0, Pearson correlation is 0, I cannot say something like this. Adding one of them maybe increase the value of the other, or maybe decrease its value. I don't know. In the future, we can see that this correlation is very important for us. We can remove correlated features. I have two correlated features. I can remove one of them and keep the other. But for uncorrelated features, I should keep one of them. I should keep both of them. For uncorrelated features, I should keep both of features. But for correlated features, I can keep one of them and remove the others because they are correlated. So it's not important for me. One of them can make a similar effect related to the other. So I can simply remove the rest of them. Okay. One of the students says that send us exercise. Okay. I will give you more exercise next week. But before of that, you should be care about the first assignment. I will give you more assignment after that. In the also in the second assignment in next 2 weeks, I will ask you to calculate some correlations between at least 2 or 3 features. I will ask you. But before of that assignment, I will give you more exercise. And also you can find some exercise in the textbook, in our textbook. You can do it. But I will give you more. Also, are there some details of your reference? It is obligatory for us to memorize them all, or are there some details? Please be clear that in this course, I don't like you memorize something. Yes, you must keep in your mind some main topics. For example, what is the difference between classification and clustering? What are the metrics for that? What is the correlation? Or something like that. But I never ask you to memorize for example, the formula of Pearson. I never ask you to keep in mind this formula. I will give you some exercise, but I never ask you to keep this, because in data mining we have several tools with lots of parameters. If I decided to ask you to keep all of those parameters, you cannot. So instead of keeping in your mind, I will ask you to do some assignment, some practical assignment during the term. Still, we have 9 weeks. Still, we have 9 weeks ahead, and so we have enough time to do more assignments. So don't worry about that. I will give you, and just keep in your mind some basic information and some major topics. Details are not necessary. Okay, is there any question?